Namaskar. This is my audio lecture on mechanics. In this lecture, I'll discuss about the Raudian mechanics. Actually, up to my last lecture, you have learnt about Newtonian mechanics, then Lagrangian mechanics and Hamiltonian mechanics. You know that Newton mechanics talks about the forces. It is based upon the four laws, which are the four laws of motion, three laws of motion and one gravitational law of motion. And the basic theme behind the Newton mechanics is that a body which is at rest or in motion will remain in its state unless and until some external forces applied on it. So this was the basic principle of Newton mechanics. When we shift to Lagrangian mechanics, we introduce a configuration space. In Lagrangian mechanics, we talk about generalized coordinates. We introduced a new set of coordinates which was known as generalized coordinate. And in that mechanics, we learned about a different approach through which the dynamical systems can be solved. Similarly, we again went through another approach which is known as Hamiltonian approach or Hamilton's mechanics. In that mechanics, we talked about the phase space. This was another approach to solve mechanical problems, and all these three mechanics have their own importance, have their own characteristics, or the situations where we should use Newton mechanics or Lagrange mechanics or Hamilton's mechanics. Similarly, Edward John Routh introduced this new approach to mechanics, which is actually called the hybrid formulation of Lagrangian mechanics and Hamiltonian mechanics. Actually, it replaces both. It replaces Lagrangian function as well as the Hamiltonian. So, it is in between the two. It is in between Lagrange and Hamilton mechanics. This Raudian or the Raud function is obtained again with the help of Legendre transformation. We discussed about the Legendre transformation when we introduced Hamiltonian. Hamilton's function was introduced with the help of Lagrange function, and there we saw that how we can introduce a new function which is Hamilton's functions with the help of Legendre transformation applied on Lagrange function. Similarly, this Raud function may be introduced with the help of Legendre transformation. This Raudian mechanics, whatever you find with the Raudian mechanics will be the same as you can find with the Newtonian mechanics. So it is the equivalent. It is equivalent to Newtonian mechanics, and no new physics is introduced by it. It is just an approach, and in some problems it is convenient to use the Raud mechanics. So it offers an alternative way to solve the mechanical problems. And basically, if I talk about what is the difference between the four mechanics like Newtonian, Lagrangian, Hamiltonian and Raudian, then basically the difference is of variables, and then the difference is of situation. The same situation may be handled with the help of Newton mechanics, Lagrange mechanics, Hamilton mechanics or Raud mechanics, but it is a matter of degree of convenience, so that we decide that which type of mechanics we should use. In Newton mechanics, we use the conventional coordinates. In Lagrange mechanics, you know that L is the basic function of Lagrange mechanics, which is known as Lagrangian, and that Lagrangian is a function of generalized coordinate and generalized velocity, right? And the variables which are not appearing in Lagrange are called the cyclic coordinates. When we come to the Hamilton mechanics, then in Hamilton mechanics we know that it is based on a function which is known as Hamiltonian, which is denoted by capital H, and that capital H is a function of generalized coordinates and corresponding momenta. So the function was depending on generalized coordinate and momentum, their momentum, while in Lagrangian the generalized coordinate and generalized velocity, these were important. In Raudian mechanics, you will see that your Raud function or the Raudian will depend upon generalized coordinate, and only the velocities of those coordinates which are not present in Raud function. Simply means that if Raud is a function of some generalized coordinates, then it will also be a function of their corresponding velocity. But if some generalized coordinates are absent from the Raudian function, then naturally it will not depend upon corresponding velocity. So there is a difference of variables in the four type of mechanics or four approaches in mechanics. When we derive the Raud equations of motion, you will see this point that Raudian equations are exactly the Hamiltonian equations for some coordinates and corresponding momenta, and the Lagrangian equations for the rest of the coordinates and their velocities. So you will better understand this point when I'll derive the Raud equations of motion. And naturally there is a question then, when the Raudian mechanics is comfortable to use or convenient to use, then naturally the answer is that if you have cyclic coordinates in your mechanical problem, then naturally if you adopt the Raudian approach, it is the simpler approach. So to introduce the Raudian function, first of all we'll define a mechanical system which is described by certain generalized coordinates. So consider a mechanical system described by, say, n plus s coordinates. You may also take n coordinates. I am taking n plus s just to give you a clear differentiation between the role of cyclic and non-cyclic coordinates. So as it is described by n plus s coordinates, that means your system of particles is described by n plus s coordinates. Coordinates q, I and q, qi and zeta j, where I goes from 1 to n and j goes from 1 to s. As I told you earlier that I am taking qi and zeta j just to give you a clear picture of the role of cyclic coordinates in Raudian. Otherwise you may take qi where I is going from 1 to n. You may consider the cyclic coordinates from these qi, but I'll do in a different manner. These are n plus n s coordinates which are describing your dynamical system, such that L, that means your Lagrangian, is defined as qi. Naturally it depends upon the velocities, so qi dot zeta j and corresponding velocity components in time. This is the Lagrangian, right? From this Lagrangian I may find dl. derivative of L, total derivative of L. First, I'll differentiate L with respect to Qi. Then total derivative of Qi dot dQi dot delta L with respect to zeta j d zeta j, then L derivative of L with respect to zeta j dot d zeta j dot delta L delta t. Here I have not put the summation symbol, but it is understood that if I am putting here summation, it is for I going from 1 to n, and if I am putting here summation symbol, it is for j is going from 1 to s. So wherever you have dummy suffix, you should put the summation symbol. Now I'll use Lagrange equations of motion. I know that derivative of delta L delta, this is Qi, this is Qi dot minus delta L delta Qj is 0. This is for a conservative system. Or delta L delta Qj is equal to derivative of this delta L delta Qi dot, sorry, this is not j, this is I, this is Pi, so Pi dot, right? So I'll use it in 2. So 2 implies dl is summation, this delta L delta Qi may be replaced by Pi dot dQi, this is Qi dot delta L delta Qi dot, which is itself Pi dQi dot plus this summation is for I, this is for I, summation delta L delta zeta j d zeta j, इसको हम नहीं छोड़ेंगे, ऐसे ही रखेंगे, j going from 1 to s and here I going from 1 to n, plus delta L delta zeta j dot d zeta j dot plus delta L delta t, right? This is also summation. So in this expression, I'll have some adjustments. This Pi dQi dot, I am adding a term, summation Qi dot dPi, derivative of Pi and Qi dot as such, minus subtracting the same term, then writing this term, this one Pi dQi dot plus rest of the term will remain as such, zeta j d zeta j summation zeta j dot d zeta j dot plus delta L delta t. Now make the combination of these two. This is the total derivative of Qi dot Pi, and take it to the left hand side, L minus Qi dot Pi. Summation Pi dot dQi then minus summation qi dot dpi plus rest of the terms L delta zeta j d zeta j L derivative with respect to zeta j dot zeta j dot L delta t. So at this stage I'll define a function R, Raudian function. Define R as, this is summation pi summation qi dot pi minus L. This R is defined with the help of Legendre transformation. So define this R. Using this R, your 4 will convert to d of R minus sigma pi dot dqi plus qi dot dpi minus summation zeta j d zeta j minus delta zeta j dot d zeta j dot plus, सॉरी माइनस होगा ये भी, माइनस डेल्टा L डेल्टा t. Now we define Raudian as a function. This is Raudian in terms of Lagrangian. So I'll define Raudian as, define Raudian as a function of qi pi zeta j dot in time. You see, in this expression your R is a function of qi. Qi are generalized coordinates where I is going from 1 to n and pi are representing the corresponding momentum. This is again generalized coordinate zeta j, and zeta j dot are the corresponding velocities. Because at this stage, while defining Raud function, I have assumed that these qi are the cyclic, which I'll use later. This property will be used later, and therefore corresponding velocities are now present in this expression. You see that R is a function of qi, but these qi will be cyclic. These are the corresponding momentum. These coordinates are non-cyclic, so their corresponding velocities will be present in R. But the velocity components corresponding to qi are absent. Okay. Just to show the relation of R or the derivative of R with respect to qi, its relation with momentum, I have written R as a function of qi. Otherwise, if qi is cyclic, it will not appear in R as well. तो वो हम बाद में देखेंगे कि कैसे होगा. फिलहाल इस राउदियन में ये हमारा था इक्वेशन नंबर 5. Now with the help of this R, again we'll find dr, derivative of R. So naturally R with respect to qi and then dqi, summation is for I. Here j is going from 1 to s. Then derivative of R with respect to pi dpi, summation derivative of r with respect to zeta j, derivative of zeta j, r with respect to zeta j dot, d zeta j dot plus derivative of r with respect to time. This is summation for I, this is for j, this is for j. Okay. Now, if you compare these two equations, one on the previous page, here the components of dqi is minus pi dot. It is minus pi dot. So comparing 5 and 7, because both are the expressions for dr and these are just the different ways to write dr. Delta r delta qi is equal to minus pi dot. Likewise, I'll compare the coefficient of dpi, which again you can see that dpi, coefficient of dpi is qi dot. So I'll get the relation delta r delta pi is equal to qi dot. Likewise, comparing d zeta j, I get delta r delta zeta j is equal to minus delta l delta zeta j. For this one, delta r delta zeta j dot delta l delta zeta j dot and delta r delta t is equal to delta l delta t. So these are the relations for r. You see, these two are the equations. These two are representing 2n equations like the Hamiltonian equations. There you have h in place of r. So these are n in number, I is going from 1 to n. So these are n, these are n. So these are 2n equations. These are relations for L and R, and since J is 1 to S, so these are S relations, these are again S relations. So these are 2S relations, and this is one relation between R and T with respect to time derivative, with respect to time. So if I say that some coordinates are cyclic, let qi are cyclic, then what will happen? Then this implies delta L delta qi is 0, right? Or pi dot is 0. And using this pi dot 0 in 8a, this is 8a, this you can see 8b, this is 8c, 8d and 8e. So 8a implies delta r delta qi is also 0. So r is not a function of qi. If qi is cyclic, it will not appear in r. So whatever I have written in 6, this qi will disappear from here. And now what about corresponding pi? You see that pi dot is 0. This implies, or you write it as, since pi dot is 0, pi is constants. These all pi are constants. So corresponding momenta are also constant. So finally in the 6, this will disappear and these will be replaced by constants. Now you see that delta r, delta pi, rqi dot, and what are pi? Pi are alpha I. So delta r, delta alpha I, rqi dot. So from here you can very well find your qi by integrating this and differentiating r with respect to this alpha I. You can very well get your qi in terms of zeta j dot and time. So finally, what is your r? In this r, you see here that in this r, these are absent, these are constants, and whatever the velocity, if there is some this qi, these are absent, but still, if why we say that these are absent, because you see here these qi are replaced in terms of these non-cyclic coordinates and their non-cyclic corresponding velocities. So finally in this r you are left with this non-cyclic coordinate and these non-cyclic these velocities corresponding to non-cyclic coordinates, right? So I'll write final r. Your r is a function of zeta j dot and time, and you know the relation, these relations, these are the relations. So what is the Lagrange equation of motion for these coordinates? For j coordinates, derivative of delta L delta zeta j dot minus delta L delta zeta j is 0. Now substitute 8 C and D. This converts to derivative of time derivative of delta r delta zeta j dot minus delta r delta zeta j. So this is the final equation, and in this equation your j is going from 1 to s. So you see that your number of equations are reduced. These are second order equations, but these are only s in number. So degree of freedom is reduced, equations are reduced. So this is the big benefit. And what is the reduction? It is the same number, it is reduced by the same number as the number of cyclic coordinates. You see that initially you were having n plus s coordinates, n was the number of cyclic coordinates, so subtract this n, and finally you are getting your s number of equations of motion, which are second order equations of motion. So this is the main benefit of Raudian procedure. Your number of equations are reduced, so your work is reduced. Now we'll see an application of this Raudian procedure. So consider a physical system. In this system I'm considering one example. We are considering a particle, and particle is moving in a plane. It is moving under the potential velocity, which is a function of a radial component, right? So a particle is moving in a plane. This is moving in a plane under the influence of potential depending on r. As it is moving in a plane, so there will be two generalized coordinates r and theta, but this and potential may depend upon r and theta both, but in this case your potential is depending on r only. Now describe the motion by Raudian procedure. Right? Now you look at the steps which we will follow. In step 1, you find Lagrangian. L is, naturally L will be a function of r, theta, r dot, theta dot, and maybe a function of time. And if I can diagnose the cyclic coordinates, I may disappear those coordinates from L. This L will be kinetic energy minus potential energy. This kinetic energy for a particle moving in a plane will be half m if particle mass is represented by m, r dot square plus r square theta dot square. This we have derived earlier, minus potential energy is depending on r, so v function of r. So this is the first step. You find the Lagrangian and decide that what are the cyclic coordinates. In this expression you can very well see that theta is not appearing, only r is there, so theta is the cyclic coordinate. One shows that r is cyclic. So if r is cyclic, sorry, theta is cyclic, not r, theta is cyclic. If theta is cyclic, this means that L is not depending upon theta, so this is 0, and this simply means that p theta dot is 0 or p theta is constant. Let this constant be a. So you have find what is your p theta. Now you should proceed with step 2. In this step, whatever is your cyclic coordinate, you try to find its corresponding velocity. That means our aim is to find what is theta dot. So for that, our aim is to find theta dot. For that, we'll use another relation, delta L delta theta dot. By definition it is p theta, and your p theta is a. You have derived from here, p theta is a. Now differentiate L, this Lagrangian, with respect to theta dot. Half m twice r square theta dot is equal to a. So it is very easy to find your theta dot. This theta dot is a upon m r square. This is theta dot. So this is second step. Now in step 3, I'll define my Raudian. R. This R is defined as, because this R is defined with the help of cyclic coordinate. Your theta is cyclic coordinate. So your R will be theta dot p theta minus L. You can see in the previous sheet that you have defined your R with the help of L. This is R, which you defined with the help of L. From this L, or from summation of this combination. This is the combination of the velocity corresponding to cyclic coordinate and pi. You look at this expression, In R, you have qi dot. Qi are all cyclic. So this is the corresponding velocity, qi dot for the ith particle, and multiplied by its momentum, which is pi. So we take all such type of combinations and then subtract L from these. So in the same way, I have defined my R. Theta is cyclic, so I have taken a combination of corresponding velocity multiplied by corresponding momentum. So theta dot p theta minus L. Now I'll put all the values. R is equal to theta dot and p theta. P theta is, I may also put the value of theta dot. Theta dot is a upon m r square, and p theta is a minus L. L is this much, half m r dot square plus r square. I have not to write this theta dot because r is not containing the velocities corresponding to cyclic coordinate. So I have to replace this theta dot also. So it is a square m square r4 and then plus vr. So you see this expression? In this expression you are just having r, which is not cyclic, r dot, which is again the velocity corresponding to this coordinate r. Otherwise you are not having theta, you are not having theta dots, and you are having these a, which are the corresponding momentum, but these are constants. So finally your r is a square. If you solve this term and this term, your r will be a square upon twice mr square minus half mr dot square plus v function of r. So you see the degree of freedom is reduced by 1 because you have one cyclic coordinate. So degree of freedom is reduced, your number of equations will also reduce. Now equation of motion for r. Equation of motion will be d dt of delta r dot minus delta r is 0. You are having only one equation because you are having one coordinate on which r is depending. Now put the values and solve. You will get a square mr cube minus u dot r minus mr double dot is equal to 0. You are having this equation in terms of r double dot. You are having this equation in terms of theta dot. These are the equations of motion. Solve these and you can find the path. So 3 and 4 are equations of motion. So in this way you can find the solution of any dynamical system, and if that dynamical system is containing the cyclic coordinates, then it is easy to use the Raudian procedure. You can solve the same problem when you are considering the motion in 3 dimension and you consider the spherical polar coordinates. So the same problem, you will do the same problem, example 1, for 3-dimensional coordinate system in which spherical coordinates are to be considered. Similarly, you can take cylindrical polar coordinates and then you can solve this problem. I may give you 2 exercises. One is that if a particle of mass m under the influence of central potential is moving, then if Lagrangian in spherical polar coordinates is given by L function of r dot theta, theta dot phi, phi dot and time is given by m by 2 r dot square, r square theta dot square plus r square sine square theta phi dot square minus Vr. Describe the motion by Raudian procedure. Right? So for practice you may also get so many questions, or whatever questions you have solved with the help of Lagrangian mechanics or Hamiltonian mechanics may be solved by Raudian mechanics. So this is all about this lecture. This is all about the introduction of Raudian mechanics and then its application. Okay, thank you.